Hi. So today I would like to record a video of a talk that I gave at CQT in Singapore on December 20th. And this talk and today I want to talk about quantum search with noisy oracle, which a couple of months ago I put a paper on arXiv. And I have some follow-up work, and in this presentation I want to talk about it. Okay, so let me briefly give an outline of what I'm talking about. So first I'll just quickly talk about the model of query algorithms and about noisy query algorithms. In particular, talk about various noise models. And essentially where I want to get in this talk is I want to give you some kind of, intuition how, if you wanted to prove lower bounds with noisy oracle, how you could go about it. And that will be the last part of the talk for a specific type of noise model. But as a warm-up, I'll talk about noiseless search. So I'll essentially quickly reprove the optimality of Grover's algorithm, meaning I'll provide the tight lower bound. And then I'll go to the noisy search. Okay, so in unstructured search, we are given access to some oracle, which evaluates some function, which is a Boolean valued function. And our goal is to find input x such that f of x is equal to 1. And we call such inputs x marked. And we are given access to this input via these reversible oracles. The oracle is a reversible operation, which has access to two registers. The first register just encodes the input x in binary, and the second one is a control which says whether we apply the phase to the first register if f of x is equal to 1. So if the second register is 0, then nothing happens to the first register. This is sometimes referred to as a phase register, while it's equivalent to what is known as a just standard oracle. So because we need log n bits to encode x, so in total this register acts on log n plus 1 qubits. Okay, so the generic search algorithm looks as follows. This is quite typical for query algorithms. We alternate between unitaries, which are completely independent from f, and which can be chosen by the designer of the algorithm and the oracle calls. And in the end, we register the query input register q and return the result. And so this is a little bit, in general, the registers used for returning result are not necessarily the same as the registers used for oracle access. But in this particular case, it will be more convenient to have to use the same register. And the reason why we can do that is because for oracle access we are querying oracle in some inputs x, and what we are supposed to return at the end is also some input. We are supposed to return a marked input. So this is just for convenience, mathematical convenience. It would completely work fine if we have used another register for the final measurement. Okay, so now let's talk about various noise models. So first, I would like to talk about what I call negligent oracle. And this is the noisy oracle considered by Regev and Schiff in 2008. So the oracle that they considered is as follows. So with probability 1 minus p, everything works fine, and the correct oracle call is applied. However, with probability p, nothing happens. And another way to look at it is that we always apply the correct oracle, and then with probability p, we uncompute whatever the oracle was doing. And Regev and Schiff showed that if we have a constant, if p is constant, then the number of queries needed for the algorithm to succeed is linear. And more generally, their proof works for any probability p. So their proof provides a lower bound omega n times p. Let me also mention why this is optimal, up to some log factors if p is close to constant. So here I have chosen these constants generously, just to kind of make sure that everything works. I think everything should work. So what we do is we 100,000 NP squared times we repeat the following procedure. So first we run a grower's algorithm for 1 over 100p iterations, and so with high probability, no error will occur, because in expectation the error occurs in 1 over p iterations, meaning oracular error. And then, we know that successive grower's algorithm scales quadratically in a number of queries. So with probability approximately 1 over asymptotically NP squared, we're going to find a solution. And we can check such solution using log n queries. If we had access to a noiseless classical oracle, this last step is essentially classical, we would be able to check solution just using one classical query. And then, what we get, accumulating all the costs, is the query complexity, essentially n times p, and potentially a log factor. Okay, so the noise model I considered earlier in this year is as follows. So here, again, with probability 1 minus p, oracle works completely as we want, without any faults. However, with probability p, we apply completely depolarizing channel on all the registers used by the query. And here, when I say completely depolarizing, it's the register which maps everything to a maximally mixed state. So you can think of it as, this depolarizing noise completely destroying whatever was in this register and replacing it by maximally mixed state. One thing to mention is that we don't consider this noise, qubit by qubit. It's either with probability 1 minus p, there's no noise at all, and with probability p, everything is mapped to maximum mixed state. And I might as well have written this noise before the oracle call, because it commutes with the oracle call, and that's not going to be the case for some other noise models that I consider next. So that's why I just want to mention that here we could have written this DP before, because it doesn't matter if you first apply oracle and then you depolarize everything, or other way around. And earlier this year I managed to prove a lower bound for this case, which is also NP. And actually the algorithm that I presented before, it will work for all, it will give NP query algorithm for all the noise models that I consider. So the same. So this is also tight up to potentially log factors. And so what's worth mentioning is that the proof by Regev and Schiff didn't work for this scenario, while for the proof that I presented earlier this year, it couldn't reprove the results by Regev and Schiff. However, actually, later in this talk, I'll talk about kind of like, I will try to reprove the result by Regev and Schiff using the extension of the formalism that I used earlier this year. Okay, so after I had this result, I had a discussion with Francois Legal, and he considered he asked me what happens if only one qubit is affected by the noise. And here, unlike before, here actually, so we can consider the scenario where the depolarizing noise affects only one qubit. And then, like before, this kind of noise does not commute with the oracle call. And the reason why I'm considering noise both before and after the oracle call is that if there was a noise only before the oracle call or only after the oracle call, and we knew which one is the case, we would be able to completely deal with such a scenario, meaning that we would still have quadratic speedups obtained by Grover's algorithm. However, if it's not the case, then I had to generalize my previous approach, and I managed to prove lower bound n times p again. And it doesn't matter whether this noise affects the control qubit or one of the log n qubits used for the index. And so what I also want to mention is that these noise models, when I consider them, this noise does not affect any of the remaining registers of the algorithm. This noise only affects query qubits used for oracle calls. Okay, So now I'll reprove the bound in the noiseless case, which, as I mentioned, will be a warm-up for the noisy case. Okay, before we proceed with the proof, let's make some simplifying assumptions. So first of all, I'll always assume that the control register is in register 1, is in state 1, which essentially means that the oracle is always turned on, it's never turned off. And of course, this kind of simplified oracle cannot distinguish between all ones input and all zeros input, but that's not going to be a problem, because we're going to make another assumption that there's exactly one marked element, and by fx we denote the function for which x is the unique marked element. And so this in some sense corresponds to the hardest cases, hardest instances of the problem. So if we have only one marked element, then how does this oracle looks like for this function f of x? Well, it flips the sign for state x, for input x, and for any other input it doesn't do anything. And there's another convenient way how we can write this operator is the identity on a query register minus twice the projector on the marked element x. And this will be useful later. Okay, so this is just our diagram of our generic algorithm as before, except now we have removed the control register because I said we're not going to be using it. So a common way to prove lower bounds, which is used, for example, for when proving adversary method, is to introduce another register which holds the truth table of the function. So before, like if we have these oracle calls f of x, we can think of them being controlled by some register which is in state fx, which tells us to which function we are making oracle calls. But this part is not accessible to the algorithm, and that's why unitaries don't extend to this space. And we can think of this controlled operation where the oracle call f of x is applied and it's controlled by the state of truth table as just one big operation O. And now it's convenient to remember that we had this O f of x to be identity minus twice the projector on x. And now if we combine these two expressions, we can write O as follows. It's identity on both the truth table register and the query register minus twice this projector on the pairs x, fx. And this projector will be very useful. Okay, so now let's just replace in our diagram this controlled operation by by big O, and this is the expression we just had. And so now what we can think of is that instead of having just a single function f of x, we can have a random function. So how can we get a random function? We can initialize this truth table register as a uniform superposition, and then just measure it right away. And that would give us some f of x. So essentially we would be running the computation on f of x, and the algorithm will succeed if in the end f of x is equal y. However, the nice thing is that this measurement that we are doing right away, it actually commutes with these extended oracle calls. So we can move to the back of the computation, and we can look at the final state of the computation, phi tau, after tau number queries, and perform this measurement on this state. And as I mentioned before, we succeed if x obtained from f of x is equal to y. So the measurement on projector on successful outcomes is just this projector that we had before, which projects on pairs of x on f of x. And here in the circuit diagram, I just have written at the end pi success, meaning that we can think of measuring according to pi success and its orthogonal complement, and we succeed if we get pi success. So as I mentioned before, success probability, it's now just simply the projector of the final state on the pi success squared. It's norm squared. So one thing that it's very useful to mention here is that if you look at it, you can actually see that O is just identity minus twice the projector on pi success. So this equality will be very useful. And we can actually look at all these intermediate states as well, which will be useful for our analysis. So state phi t is just a state right after we apply unitary ut. So it is essentially the state after t oracle calls. So initially phi 0 is just a uniform superposition on truth table times some input independent state on the algorithm side, and then every other phi t plus 1 we can define recursively, which will this expression, recursive expression, will be useful later. Okay, so it will be convenient to have a notation for this initial uniform superposition, which we will just call u. Okay, so now we put this u in our circuit diagram, and now to measure the progress of algorithm, we want to somehow have a way to measure how the algorithm progresses towards successful outcome. We will just look at the truth table, and we'll define two projectors of on the corresponding space. The pi a just projects on this vector u, and b projects on its orthogonal complement. And we can think of these projectors, to also acting as identity on all the other registers, in particular the algorithm registers. So even though we're not going to write it explicitly, these projectors act as identity on all the other spaces. And we define the progress measure psi t as the norm of the projection of state phi t on pi b. So it's easy to see already from this diagram that initially the progress measure is 0, because the initial state of truth table is u. Then I'll show that the success probability is essentially at the final value of the progress measure is essentially bound on the square root of success probability. So more precisely, we'll show that the square root of success probability is no more than psi t plus some small additive term. And the third step, which will be the most involved, to shows that a one oracle call cannot extend this progress measure by more than 2 over square root of n. And then if we combine all these three claims, we can see that the success probability is no more than number of oracle calls squared over n, and we know that this is optimal. Okay, so now I should talk about how success probability relates to that progress measure. So recall the definition of success probability, that is just a normal projector on successful outcomes. And now just before the state phi t, we can put an identity and then expand the identity as the sum of projectors pi b plus and pi a. Next, we apply a triangle inequality, and then we apply this inequality, which I'll be using explicitly or implicitly quite often, which tells that the spectral norm of the product of matrices is no more than the product of spectral norms of those matrices. And now we have 4 norms, and we can evaluate each of those norms separately. So, pi success is projector, so its norm is 1, and phi t is a unit vector, so its norm is 1, so that's easy. As for this norm, it's just a progress, it's just a final progress measure, psi tau. It remains to evaluate the norm of projector pi success and pi a, and let us see that it is 1 over square root of n. So first, what we do is we just put the definitions of these projectors, and here for pi a, I have also written that it acts as identity on iq, just for clarity. So now we can look at these vectors fx and u, which is a uniform superposition over all fx's. So of course the inner product is therefore 1 over square root of n. So we just get this equality. And now if we look at the sum over the norm, because of this second register, which is in state x, all the terms under the sum has orthogonal images and co-images. So that means just all of them, we can think of it as we are essentially taking a norm of a block diagonal matrix. So the norm of this matrix under the norm is just 1. So we got our desired inequality, which relates the success probability to the final progress measure. So now we are just left to show that how the progress measure evolves per one query. So progress measure psi t plus 1 after, this is just a definition of it. And again, as before, we can, well, actually, first, what we do is we put this recursive definition of state psi t plus 1. So we take state psi t, apply the oracle, and then a unitary. And this unitary, because it acts on completely different registers than pi b, because pi b acts non-trivially only on truth table, while u acts non-trivially only on algorithm registers, they commute, and because they commute, we can, applying unitary to some matrix does not change its spectral norm, so we can just remove this u. And then, as before, we expand, we can think of inserting the identity after O, and then expanding it as sum pi b plus pi a. Then, as before, we take a triangle inequality and use the fact that the norm of product of matrices is no more than product of norms of those matrices. So this is just as before. And as before, we have 4 norms to bound. So the side terms are, again, they just have norm 1, similar as before. Okay, so then this term is just a progress measure after t steps. And this remaining term will show that its norm is no more than 2 over square root of n. Okay, now remember that we were able to express extended oracle O as the identity minus twice pi success. So we just enter that expression here for the extended oracle call. And so because pi b and pi a are orthogonal, because of them this identity term will vanish. And we are left with twice the norm of pi b success pi a. We can, remove this pi b term because its norm is because its norm is 1. And now we are left with twice the norm of pi success pi a, and we already bounded it before when we analyzed the final, the relationship between success probability and the final progress value. And so we are left with 2 over square root of n, which is what we needed. So this concludes the proof of the third step, stated the claims that we make about this progress measure, and in turn it concludes the proof of optimality of Grover's asymptotic optimality of Grover's algorithm. Okay, so now let's talk about noisy search, and what I'll do is essentially I will reprove the bound by Regev and Schiff, skipping a few details, but hopefully not too many. But instead of using their proof for the proof, I will use the methodology, which can also handle this, depolarizing noise. Okay, so first, so recall that negligent oracle. So with probability 1 minus p, it applies oracle correctly. However, with probability p, it doesn't do anything. So we can write this negligent oracle as a completely positive trace preserving map, or in other words, a quantum channel, which has these 2 cross operators, gx0 and gx1. And so, as before, we can think of that, we have this oracle, noisy oracle on the algorithm side, and we have some truth table which contains a register f of x, which tells us which oracle to apply, for which function to apply the oracle. However, now we will introduce another register, which we call environment register, which in some sense, what it will do, this new register, as per Steinspring's representation, will purify this non-unitary operation OFX pi. It is well known that non-unitary operation on some registers can be thought of as a unitary operation on a larger space. Normally we could think of this environment register starting in some state 0, but we can also think of this larger operation O tilde p as just being a linear isometry, which maps all states on truth unit vectors and truth table and algorithm to unit vectors in this larger space. And in particular, this O tilde p can be written as follows. Can be defined as follows, where we have this on truth table, we have this register f of x, which controls what we are doing, and then we have these registers. We have these states in the environment register 0 prime and 1 prime, where 0 prime means that on the algorithm side the oracle was applied properly, while 1 prime means that there was an error. But of course the algorithm doesn't have access to these states. And it is easy to see that from point of view of truth table and algorithm, these two circuit diagrams are indistinguishable. And as before, it is worth remembering that we have this nice expression for the noiseless oracle called identity minus twice the projector on X, which we will use on next slide. Okay, so this is just the expression that we had for O tilde p, and here for cross operator gx0, I have put this expression for noiseless oracle call as identity minus twice the projector on X. However, these are not actually the most convenient cross operators for our purposes. And that's why I have named these bases of environment 0 prime and 1 prime, because we can have this other basis 0, 1. And if in the above expression for O tilde, we enter these expressions for 0 prime and 1 prime, and then we collect together terms corresponding to state 0 and state 1, we get these new cross operators, kx0 and kx1. And there's a more direct way how to argue this, is that when we are having a cross representation of an operator, if another set of cross operators is obtained as a unitary combination of the first set, then the two sets of cross operators correspond to the same completely positive trace preserving map. So this is essentially just another way of writing that. So now we have this bottom expression for O tilde pi, and this is going to be an expression that we'll be using. So now essentially, if you look at these two cross operators, what we can see is that the bottom one says that with probability approximately 4p, we can think of this operation as measuring to the query register to the successful outcome x. And in some sense, even though the algorithm doesn't know that this has happened, when it happens, for sake of measuring progress, we will assume that the algorithm knows that it has succeeded. And I'll talk about that later. And now we have this other cross operator, kx0, which essentially just, it's kind of almost like this noiseless oracle call, except, there's this, for state x, we are losing some of the norm. Okay, so now we can write, our extended noisy algorithm as the following diagram. So again, we alternate between unitaries and these extended oracle calls. We have the truth table, which is initialized as a uniform superposition over all functions, and we have an environment register, which starts empty, and then every extended noiseless oracle call extends 1 bit to it. And as before, we can look at the states of this computation at various stages, and using these states, we'll define a progress measure. So if you recall, before we had these two projectors, pi a and pi b, and now we'll have their new definitions will be almost the same, except now we have to also look what's happening on an environment register. So for pi a and pi b, we'll define them when the environment register contains only zeros. So essentially, at no point this noisy oracle call has collapsed the query register to the correct solution. So far, that's why in the register there are only zeros. And then we also have the register by C, which tells that the environment contains at least one entry 1. And so intuitively, these registers pi c corresponds to the scenario then when we can think of that we have found a solution, and we have found the solution using in some sense in a classical way, because we have collapsed the query register to the correct solution. Pi b means that we have found a solution in a quantum way, meaning we haven't collapsed we can think of us not having collapsed the computation, while pi a essentially corresponds to the scenario when we haven't made any progress. Okay, now we want to define these progress measures again. And so the first candidate would be, as I mentioned, since these projectors pi c and pi b corresponds to us having found a solution, we might think of defining, this progress measure as projection on the corresponding space. However, this is actually not going to be very useful a progress measure, and the reason is that it is easier to work with progress measures if for every step of the computation we can bound this progress measure, the increase in progress measure, by a specific amount. However, in this scenario, at the beginning, this progress measure will be able to increase by quite large steps, but later, it's not going to be the case, and that's why a much better candidate for progress measure would be the following, where we would define this progress measure as a square of this vector, of the norm of this vector, and then because the images of pi c and pi b are orthogonal, we can just express in this form. However, this still actually will not work, and we want to do a slight modification. If you recall these cross operators kx0 and kx1, if you look at this cross operator kx0, we can see that in front of x there's this factor 1 minus p, which means that essentially because of this cross operator, some part of the state, some part of the overlap of the state on space pi b will go away, and the more overlap we have there, the more will go away. And in some sense, by going away, it will actually go from space corresponding to pi b to space corresponding to pi c. And in some sense, even though both of them correspond to algorithm having made some progress, in some sense, the space pi b is better, because that means that we have made quantum progress. Because once things become classical, we know that search classically is much slower than quantumly. So in some sense, it's better that we are in this space pi b. And for that reason, we've actually put a positive constant in front of this term pi b, the norm squared of pi b phi t. And I think any constant above 1 works, but because we're going to be quite loose in our analysis here, I'll choose the constant gamma equals 6 here. Okay, so this is our final progress measure. And again, as before, we'll prove 3 things for it. First, we'll show that initially the value of this progress measure is 0. Then we show that the success probability is no more than a final progress measure plus 2 over n. And the third step, which will be the hardest to show, is to show that this progress measure psi t plus 1 is no more than psi t plus something that scales something asymptotically as 1 over np. And again, combining all these 3 steps, we can see that the final success probability is no more than a number of queries over np, which means that if we want the success probability to be constant, we need at least np number of queries. Okay, so as I said before, the first claim is easy, and for the second claim regarding success probability, there are actually no really new ideas compared to what we did before for the noiseless case. So I'm just going to quickly show one slide, which is, you can go through the details if you want to see that, indeed we get the claim. But it's essentially what we had before, so I'm not going to spend much time here. So now it is left to show the third claim, which tells by how much a single oracle call can increase the progress measure. So recall this expression for pi b. So we can think of the space corresponding to this projector pi b, and we will decompose this space into two parts, one which I call the active and one which I call the passive. And let me talk a little bit about the intuition behind these two spaces. So suppose we are running a Grover's algorithm for a while, and suppose there are no errors, and we have accumulated, some progress, meaning that we have some superposition, which has, increased overlap on the successful outcome, and we kind of, we become afraid that the noise might corrupt this state. So can we preserve this state from noise? And the answer is yes, we can, because the noise is affecting only the registers used by query. So if the state that we want to protect, if we just copy it to some other space, it's not going to be affected by noisy oracle calls. However, what happens in this case is that yes, we have obtained some progress, and we can protect this progress from noise. But in some sense, that means that the new progress that we make cannot get advantage from this progress that we made earlier. I guess another way to look at it is that if we look at the analysis of Grover's algorithm, the steps towards success probability in terms of a number of in terms of probability, not the amplitude, became larger and larger the further we proceed in the computation. However, if at some point this quantum state that we had managed to compute with a partial progress, if we took it aside and started from the beginning, these steps would be small again. And yet another way to look at it is that it is known that Grover's algorithm cannot be parallelized, and that's essentially because of those kind of things. So something similar happens here, that yes, we can have this partial states which has some partial progress. We can put them aside and protect them from noise, and that's what if we have such kind of states, we can think of them being passive, because they are not affected by noise, but they also don't contribute much to the increase in progress. However, if we do want to increase in the progress, in some sense we have to risk. We have to take the state that correspond to this progress, and we have to put it through the oracle. And sure, we risk that the noise will affect it, but also we will our chances of increasing the progress are also higher. And this in some sense corresponds to these two spaces, P active and P passive. Okay, so now let me actually talk about how to define them. So here I have expression for pi b, as we had before. On the truth table register, it's orthogonal to the uniform superposition over all the functions f of x. And then we also have this lambda AB, which means that the environment contains only zeros. And this lambda AB we're not going to touch throughout this slide, so just don't pay much attention to that. And also it acts as an identity on everything else. So now we will define these projectors P active and P passive, and they will be sum up to pi b. And here I also written that pi b acts as the identity on the query register, because the interesting thing about these projectors P active and P passive is that they will actually not act as the identity on the query registers, and but that still is not going to be a problem. So for these particular projectors we cannot commute them, for example, with unitaries ut, because they both act non-trivially on register IQ, but that's not going to be a problem. We'll start first by defining P active, and first let's just write another expression where for this we have inserted a formula for pi b, and we have expressed this IQ as just a sum over all states x. So that's just expanding the identity. Okay, so how do we define P active? Well, first let's define the approximation of phi x. So this is going to be state on a truth table register, and it is in some sense the closest state to fx, which is still orthogonal to uniform superposition. And it's actually not too hard to check that it is indeed orthogonal to uniform superposition. So this state with amplitude square root of n minus 1 over n is fx, and with amplitude 1 over x, it is a uniform superposition over all fy such that y is not equal x. And the second state, it will be convenient to call it u not x. So uniform superposition, everything except f of x. And then we define projector pi b active as the sum over all approximations of f of x, x, and this lambda there. And then pi b passive is just pi b minus pi b active, and this is the expression we get. But now it will be convenient to rewrite this projector pi b passive in another form. And for that, we can look at the two-dimensional space spanned by uniform superposition u and approximation of f of x. And we can see that it is the same space as spanned by u not x and fx. And this latter expression will be more useful for us. Okay. So now, we have these four projectors that we define. So here's the expressions for them. And we have this extended noisy oracle call, which we have an expression for which we have expression using cross operators. And now, using these expressions, we will have 7 claims. And I'm not going to go into detail of these 7 claims. I'm just going to very quickly talk a little bit about them. We can divide these claims into 2 groups. So the first group is claims 1, 2, and 3, and the second one is 4, 5, 6, and 7. So let me just first talk a little bit about the first 3 claims. So the first claim essentially says that if you have a 1 somewhere in an environment, then it will always stay there. And in other words, we cannot escape this space pi c by oracle calls. The second claim says that if we get to this space where we have some 1 in the register, then if we already had it in a register, or we didn't have it in a register before, so didn't have meaning that we were in space corresponding to B or A, then these 2 scenarios will have orthogonal images. So the operators corresponding to these 2 scenarios have orthogonal images. And the third claim says that the space B passive is invariant under the oracle calls. So it means 2 things. That first of all, if we are in this space, then after applying the oracle call, we remain in this space, and vice versa, we cannot get to this space from any other space. In some sense, that it means that throughout our analysis, we will be able to completely ignore this space B passive. Okay, and then we have claims 4, 5, 6, and 7, which just evaluates some norms where we have some projector, we apply this extended oracle call, and then we apply another projector. And I've written all of them in equality form, because for me, if I see an equality, my confidence that I could verify it are higher than if I see it in an inequality. So there's these expressions for these projectors are not that complex, and for these cross operators, so if you would just sit down with a paper, it wouldn't be too hard to verify these last 4 claims. But I will only consider inequality forms of them for this proof. So and for this, all of them hold, all except the second one hold for all values of p and n. But for the second one, I'll assume that p is no more than 1/3, and n is at least 4. If p is very close to 1, then this term 1 minus p has to be taken into account. But I'm not going to analyze it here. I want to mention that it works, even when p is very close to 1. But I'm going to skip that in this talk. Okay, so now having these 7 claims, where for the last 4 I'm going to use only the inequality form, I'll quickly sketch how to conclude the proof. Okay, so let's look at our progress measure after t+1 oracle calls, and this is just a definition. And as before, we use the recursive expression for the states psi t+1, so we insert here. As before, this unitary is ut+1, commute is pi c and pi b, so we can remove them. And then after we have removed them, then we can proceed by composing this projector pi b into active and passive. And we couldn't do it before we removed the unitary because, as I mentioned before, b active and b passive does not commute with u, but simply pi b does. Okay, so after we have removed this u, we decompose b, and this is what we get. And here we have also used the fact that images corresponding to b passive and b active are orthogonal. Okay, and now let's, we have these 3 terms. Let's simplify every single one of them. So for the first one, well, first, as before, we actually use, we expand the identity as a sum of projectors A, B, and C, but we can ignore the passive because, B passive, because from there we cannot get to the space corresponding to space C. Okay, and next we use the claim 2, which tells that the images of these terms are 2 terms under the norms are orthogonal. Therefore, we can use this equality. And finally, because of claim 1, we know that if we were in a state, if we were in space C, we remain in space C, so we can remove this one projector. And then, because all tilde p is a unitary, it also does not affect the norm. Okay. So now let's evaluate the second term, and the second one is easy because the passive space is invariant under the oracle calls, and again we can remove this after we commuted pi b passive and O tilde. We can just remove this O tilde. Okay, now let's address the third term. And here, again, as before, we can ignore the passive space, which I haven't written here. And we know that because of claim 1, we cannot get to the space B if we started in space C. So now, when we insert the identity before the state phi t, and then we expand it as a sum of projectors, we only have to consider projectors pi b active and pi a. And then we will subtract and add this term. And we do it so that if you look at the final expressions, and here I have these 3 things circled, we can see that the sum of these expressions sum up to the progress measure after steps t. So, so here at the very top, I have written expression for progress measure after t+1 steps. And so, there's 3 terms. And now when I expand these 3 terms and I sum together, what appears in that sum is the progress measure after t steps. So now, if you combine everything together, what we see is the increase in the progress measure can be written exactly as this quantity, and this is the quantity that we want to bound. And so here, well, first we apply some triangle inequalities. And so we get some norms, and then we bound these norms using these claims that we had for 4, 5, 6, and 7. And this is what we get. And now if you look at the, if you want to look at what is the coefficient after expanding these things corresponding to norm squared of pi b active phi t, then we can see that this is the expression for it. And remember that here I assume that p is no more than 1/3. So what we want is that we want this this coefficient to actually be negative, And that is why we choose gamma sufficiently large. In particular, as I said, in this case, gamma equals 6 works. And now we can see that the above expression can be further bounded by this quantity. So we have minus something squared plus 96 over NP. And of course, because of this something squared is minus something squared is non-positive, we get that this bound is 96. I mean, this difference is no more than 96 over NP, which concludes the proof of this third claim regarding the progress measure, and actually concludes the proof of the lower bound on the noisy search of this negligent oracle. One thing that, if you look at the term in the big parenthesis, it essentially says that, if we want these large steps in the progress measure, we need that this norm of the state projected on B active has to be asymptotically 1 over p squared of n. And this is exactly, the kind of norm that we get if we run the Grover's algorithm for 1 over p steps. And this kind of gets back to, when I mentioned that earlier, I mentioned this algorithm, which shows that the optimality of the lower bound. And this in some sense corresponds to that, meaning that if you want to make these big steps, it says that we indeed need to run Grover's algorithm for approximately these, 1 over p steps. And with this, I would like to conclude this video presentation. I hope you found some value in it. And if you have any questions, feel free to reach out to me through any channels. Yeah, thanks.